Conceptual design often starts with looking at several alternatives for the building's size, shape, massing, and orientation. And in Autodesk Revit, a great way to compare different alternatives is to use design options. Let's switch to the Manage tab and open the Design Options tool. In the Design Options, we can create an option set for comparing the different conceptual design alternatives and give that a more appropriate name. Then within that option set, let's set up several different options for comparing different designs. We'll call those Design A, Design B, and finally Design C. With this framework set up for comparing the design alternatives, we can now turn our attention to modeling the massing and shape of the different options we want to consider at this conceptual design stage. Conceptual massing is a great way to compare conceptual design alternatives because you can quickly create models with different massing, size, and shape and compare them to find the best alternative. To create conceptual masses, you have several different options. In Revit, you can go to the Component tool and choose Model in Place if you'd like to create a mass just within this project. But a better approach is to create a conceptual mass family, and the advantage is that with conceptual mass families, you can add parameters to quickly change the size and shape dynamically and test options very quickly. To create a conceptual mass family, you can go to the Revit menu and choose a new conceptual mass, or if you prefer, you can use Project Vasari. It has many of the same capabilities available in that application too. Choose the mass template, say OK, and we'll open the conceptual massing environment where we can create our new mass family. The conceptual mass editing environment is very similar to the project environment, but the background is shaded gray to let you know you're working with a special tool. The techniques you use for creating masses in the mass editing environment are very similar to the ones you use when creating in-place components. We can draw profiles on a work plane and then extrude, blend, sweep, or rotate them to create different forms. Choose the Rectangle Drawing tool, then select that we'll be drawing on the work plane. If we move down into the drawing area, we can use the intersection of the two reference planes as the point of origin for our profile. The advantage of doing that is that it'll serve as a point of reference when placing the mass family in our project. We'll draw the profile and complete it. Then we can go through and select the profile and choose to create a solid form from the Create Form tool. The form is created, and we can now start deforming and reshaping it to meet our needs. For example, one thing we can do is start to push and pull on the form using the arrows when we select a surface to go through and change the shape of the form. We can choose any of the surfaces and push and pull to make things wider or narrower. We can also choose surfaces and use the temporary dimensions to precisely control the location of the different surfaces. You can not only move the surfaces, you could also move the edges. So for example, if I choose the rear edge of the top surface and push or pull it, we can deform the form in that way. To create a more complex form, we could add additional solid forms or void forms to continue changing the shape of the mass. For example, we can choose the Rectangle tool and this time instead choose to draw on the face of one of the surfaces, then draw a rectangle on the front face. We'll choose that rectangular profile and create a solid form, then pull that out to create an extension to that face. If you'd like to carve away part of the mass, you can use a void form. Let's choose the Circle Drawing tool. Again, we'll choose to draw on the face, and this time we'll draw on the upper surface. We'll get right on the corner, then pull on out to create a circular profile. Then we'll choose that profile and choose Void Form using the Create Form tool. This time we're given a choice to create either an extruded form or a rotated form. We'll choose the extruded form. Then Complete. to carve away that corner of the conceptual mass. If we want to change the shape of that void form to carve away more or less of the conceptual mass, we can choose the void, then either adjust the temporary dimensions or choose one of the surfaces, and push and pull to adjust the void form. When we complete, the form will be adjusted as desired. Let's save this conceptual design Let's save this conceptual mass family. And then load it into our project. By default, masses are hidden in Revit projects. This warning is telling us that masses will be shown so that we can see the results of our work. Let's close that. Then we'll switch over to one of the design options, Design A, and we'll choose to place this mass object on the work plane. We'll bring it in, place it, right about here. Then let's look at it in the 3D view. We've placed our conceptual mass family for design option A. We can now create additional conceptual masses and place them as design options B and C, so we have several different alternatives to compare. One of the key advantages of working with conceptual mass families is that you can add parameters that let you quickly change the size and shape of the mass. Let's open the Level 1 floor plan view, where we can add some reference planes and parameters that'll let us control the shape of our geometry. We'll add a reference plane on the left-hand side that'll let us control the overhang on that side of the building. We'll add another reference plane on the back of the building that'll let us control the building depth. Now, when working with parameters to change the shape of your geometry, it's important to first place reference planes, add parameters that control the reference planes, and finally lock the geometry to those parameters. Let's add a parameter that will let us control the overhang on the left side of the building. We'll start by adding a dimension between the reference plane we're using as the origin of our model and the reference plane we've added to control that. We'll choose the dimension and add a parameter. In this case, we'll call it building overhang. And we'll make that an instance parameter so we can change that for every instance of the model that's placed in our project. Similarly, we can add another dimension that'll let us control the building depth. We'll choose the dimension tool, choose the reference planes, then choose the dimension and assign a parameter to that, calling it building depth. Again, this will be an instance parameter. Having placed those two reference planes, we're now ready to lock our model geometry to them, and we'll do that using the Align tool. Use the Align tool, click on the reference plane, and lock the rear of the building to that. Similarly, choose the reference plane on the left-hand side, choose this edge of the geometry, and lock to it. Okay, and now we're ready to go through and flex our geometry and see that the building model will adapt with it. Let's open the Family Types dialog and test out some of these new parameters. For the building depth, let's try entering 180 and see if the building stretches towards the rear. 200. Very good. Now let's go ahead and try changing the overhang. Currently it's at about 147. If I change that to a very extreme overhang, say 200 in that dimension, it stretches that way. If I give it a much smaller number like 120, it pulls back. So we now have a parametric model that we can place in our project and quickly vary by changing its parameters. Parametrically controlled conceptual masses give you the ability to quickly test many different options. For example, let me open a parametric family which is a little more complicated. In this case, it's something that's representing a twisting tower. And if we look at the parameters that are available in this mass family, you'll see that we have an awful lot of control to test different options. For example, in this family, we can change the size of the building top, the building base, the height of the building, as well as the twist on the building. And let's see what that could actually look like. For example, if we want to change the building height, let's change it to a 300 instead. If we want to change the building base so it flares out more like a pyramid, we can change it in a single direction, okay, or in both directions. We could also go ahead and change the building top to make it much more like a pyramid, and even change the degree of twist. For example, maybe 80 degrees as opposed to 45 degrees. And let's make this twist more visible by changing the dimensions of the top and bottom to a more rectangular shape where the change will be a little more apparent. We'll make that 100 by, say, 40, and at the bottom make that 100 by 40 also. So as you can see, conceptual mass families give you great flexibility to quickly test different options. We've loaded our conceptual masses into our project file as design options, and we're now ready to start quantifying and analyzing the masses so we can produce our conceptual estimate. We'll use Revit's Mass Floors tool to break our conceptual masses into individual floor levels and then report the area, volume, and perimeter of each of those floors to build our conceptual estimate. Start by selecting the conceptual mass, then choose the Mass Floors tool. You'll see that the mass floors will only be created for the floor levels that are defined in the project, so let's cancel out of that, and we'll add more floor levels to cover the full height of the building. Let's change to an elevation view, where we can look at the existing floor levels. You'll see that currently there are only 2 floor levels, and if we'd like to add more floor levels, what we'll do is use the Level tool and offset to create new floor levels with the same floor-to-floor height. We'll choose the Pick Line tool, enter an offset of 10 feet, and then hover over the existing floor levels to create the new ones. We could also use the Array tool to create many floor levels with a uniform spacing very quickly. Having created the floor levels, let's return to our 3D view and choose the Mass Floors tool once again. Now you'll see that all the floor levels are available for creating mass floors, so let's choose them. Then we'll say OK to create the mass floors, and you'll see that the mass is divided up into a series of plates representing each of the different floor levels. If we choose any of the mass floor elements, you'll see that the floor area, the floor perimeter, the exterior surface area, and the floor volume is reported as an instance parameter for that mass floor. And the information reported in these parameters will be the basis for our conceptual estimate. To summarize the information about all of the mass floors in a convenient form, let's create a new schedule. Switch to the View tab. Let's create a schedule. And the category we'll be scheduling is Mass Floors. For each of the mass floors, let's put the level, the area, as well as the volume. To make the schedule a little easier to read, let's sort based on the level. We can add a grand total line to sum up the areas. Then we'll switch to the Formatting tab and actually choose the floor area and say that we want to calculate a total on that. Let's make that right aligned. We'll say OK and take a look at the schedule. In the mass floor schedule, you can easily see the variation in the floor area for each of the different floor levels. And we'll be using these floor areas to compute a simple conceptual estimate by applying $dollars per square foot to each of the floor levels. Let's return to our mass floor schedule. You'll see that I've formatted the floor area and volume fields to make the values a little more readable, and now we're going to add a formula to the schedule based on some historical data showing that building this kind of facility costs approximately $200 per square foot. To add that formula, let's return to the fields, and we're going to add a calculated value. We'll call that value cost estimate, and we'll add a formula which says that we're going to take the floor area and multiply it by $200. We also have to divide by square feet just to normalize the units. When we say OK, you'll see we have a value there. Let's format that field so it's a little easier to read. We'll choose the cost estimate field and format that using a currency format. Group the digits. Let's right align it and also add a total to that field. And now we have a conceptual cost estimate based on that $200 per square foot rule for similar buildings. If we have more detailed historical data, we can refine this estimate further. For example, if we have a different figure for parking versus office space versus retail space, we can build a conditional formula to apply a different dollar per square foot figure to each of those different type of areas. Let's take a look at how that would be done. Let's return to the fields, and we'll start by adding a parameter to let us encode the usage of each of the different floor levels. We'll call this the floor usage type. It'll stay as a common field. We'll make it a parameter of type integer and say OK. So we'll use this field to encode a type 1 for, say, parking, 2 for office, and 3 for retail space. Next, we'll add a calculated value that uses that parameter. We'll call this cost estimate by usage. It'll be a number, and the formula will still use the floor area, but rather than multiplying that by a simple $200 per square foot, we'll multiply it by, rather than a simple value, an if condition. Let's take that usage type and say if that usage type is equal to 1 for parking, we'll use a value of 100. Otherwise, if it's not equal to type 1, let's add another if condition. And if it's not equal to type 2, let's check to see if it's equal to type 3. If it is type 3, we'll use a figure of $200 a square foot. Otherwise, we'll use a 0. Let's close those parentheses. And remember to divide through by the square foot so we can normalize the units. Say OK, OK. And we now have two new columns in our schedule. If we enter a floor usage, for example 1, you'll see that we compute a cost estimate based on the figure of $100 a square foot. Let's enter another 1 at level 2, another 1 at level 3. At level 4, let's switch and change to type 2. And type 2, and finally type 3. And what you'll see is that the values we're getting vary because they're using the different dollar per square foot figures based upon the usage type. So this technique is creating a more refined estimate of the conceptual cost based upon the floor usage data we have. I've formatted those fields to make them a little bit easier to read. So as a final step, let's now take this schedule and rename it. Then we can associate this schedule with a specific design option. We'll choose option A. Now we can find the schedule in the project browser and duplicate that schedule. We'll open that one instead and change it to be for option B. To switch it to option B, we'll again choose the visibility graphics and adjust the design options setting to point to option B instead. You'll see we have the data from the other conceptual mass that we're considering reported in the cost estimate, so we can compare the two. As a final step, let's create a new sheet view that will allow us to compare these different options side by side. We'll create a new sheet using the standard title block. Let's start by putting 3D views of the different design options on the sheet by dragging them in side by side so we can compare them. Then we can also drag in the cost estimates to compare them side by side too. We'll place that one under option A and that one under option B. Now if we zoom in on option B, you'll see that a very nice feature about using the conceptual masses to go through and do the estimate is that we can choose this view and activate it. Select the conceptual mass, and then change its parameters. So for example, if we want to quickly test what the effect would be of changing the building depth, we could do that. We'll see the revision to the 3D view, but we'll also see the revision automatically updated in the conceptual estimate. So we get very quick feedback and can test different options and get the feedback we need to make better design decisions.